could do is just try to explore if we find some examples that we can get inspiration from. Because I'm tired of just tweaking parameters in here. It just really doesn't feel like it's taking me anywhere. I almost get the solution, right? I get something. I get like almost a solution. Because I'm getting Python x2 1a thing here. So I think I'm getting I'm basically getting almost a solution. It's like it's the form is good. It's like the alpha divided by pi, but then the powers don't match, right? And so yeah, the powers don't match. But let's see, I mean, a free particle. So we're talking about free particles. Maybe there's something else that I'm missing here. So step back a little bit. A free particle. So normalization of a free particle. We know this is some, or at least based on what ones I read in one of the tweets that I made about these. Someone's like talking about decay. Free particle. Decay normalization or something like that. Like it doesn't normalizing the solution to free particle Schrodinger equation. Let's see what we get out of these. Can you normalize a free particle? For all we know, free particle delocalize. This cannot be normalized. A free particle. Maybe there's something in here that helps me understand these. Let's see. So we obtained the Schrodinger equation, the Hamiltonian, kinetic energy. Okay, I mean that's fine. I want to get to the point where we have the solution. So equations which crystallize because the operator is equals the second derivative. Where can simplification, the is kinetic energy. Okay, look at this. That's good. That is good. That's actually finally what we have. This is I think roughly, A is the n, and then we have this stuff. But in our case we assume, I think, that it's just k is real, right? Yeah. So the constants a plus a minus result from the constant of integration. Remember, some physical constraint is imposed upon the solution. Such a constraint is called boundary condition. The boundary condition is fashion must be zero at the boundaries where the potential energy is infinite. The free particle does not have such a boundary condition because the particle is not constrained to any one place. Another constraint is normalization. This is what we're looking for, and here the integration constants serve to satisfy the normalization requirement. Okay, let's do these. So, okay, normalizing the wave function of a free particle. We use the normalization constraint to evaluate. Yeah, okay, fine. That is, but this is it's like one dimension, right? So since the integral overall is infinite, it appears that the wave function cannot be normalized. We can circumvent this difficulty if we imagine the particle to be in a region of space ranging from -L to +L and consider L to approach infinity. The normalization then proceeds in the usual way as shown below. Notice that the normalization constants are real even though the wave functions are complex. That's an interesting thing. Really? So is that a statement? Notice that the normalization constants are real even though the wave functions are complex. They don't have to be, right? Normalization it's real. Anyway, let's not get sidetracked. So Okay, so I mean that is fine. There's actually, what am I doing? This is pretty much what I've been doing, right? So this is this. Take the constants out. Then you know. Then do this thing, right? So this is the two exponentials left. Yeah, but that's kind of one dimension. So that's kind of one dimension. That doesn't help me. And I think the rest here is just okay, the rest is just useless. Let's see what they do here. So one-dimensional free particle, three-dimensional free particle, normalizing three-dimensional free particles. Quantum physics workbook for dummies. Should be probably doing this one. But this is 1D, so that's what we're doing. Can be corrected. For finite intervals. Finally sized box. So the solutions of type so-called Fourier components are not normalizable to 1. Though they are widely used in quantum theory, they are normalized, quite improper expression, to Dirac. Usually there is a function of k becomes this. But don't worry, the free components are an idealization. They exist in nature, are wave packets, blah 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 blah. I don't know. What the fuck? That is even worse. I have one-dimensional free particle Schrödinger equation. You have this general solution. Yeah. We have a free particle, and that's the state. And this is a real parameter. Maybe indeed I shouldn't be using infinite in here, but maybe. But maybe yes. Free particle. something about normalizing free particles. Okay, look at these. That is interesting. It turns out quantum physics workbook for dummies can be useful. Going circular in 3 dimensions, spherical coordinates. Answers to problems on 3D spherical coordinates, page 175. Taking the 3 dimensions with spherical coordinates, dealing freely with free particles in spherical coordinates. Maybe. So it seems, but this is just it just making it worse, because why am I all the time thinking about 4 dimensions, as in like the stuff that's being, you know, something that's needed for 4 dimensions. So dealing for page 100, is this book, you actually have to buy it? Oh god, maybe can I just, is this, it seems like it's accessible, so I want to go to chapter 7. Or is it that this is not available? 167, page 167. Because it's going through the page 167. State vectors. Page 167. It doesn't look like I have access to the whole thing. I'm not showing this preview. That's just a preview. But maybe if I okay, spherical coordinates seems to be what is being taught in here. So solving problems in 3 dimensions. Free particles in spherical coordinates. There you go. Maybe some more information is going to be found here. I'm trying to understand free particles in both Cartesian and spherical coordinates. So free particle going in, say, x direction, some energy E, we know the wave function is like this. Now let's do the same calculation in spherical coordinates and derive the wave function in spherical equations the following form. Now the angular part, the constant angular momentum, blah, 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 blah. Now I know that theta and phi, and hence, now clearly just by substituting r with x, I'm unable to recover my Cartesian solution as described above. Moreover, solution below that which is inhabiting the Cartesian solution. I don't understand this dilemma. So technically, a spherical coordinate system is defined in three space, except the origin. Therefore, spherical coordinates are a poor description of the systems at the origin. The free particle itself has no beef with the origin. There is no actual physical boundary conditions in the origin. The moral is that we shouldn't use the spherical coordinate system to describe a translation invariant system, since it visually distinguishes a point of the system. Now say that we nevertheless choose to use spherical coordinates, so we have to give out the description r equals 0. Hence, we're effectively starting the free particle on r3 minus 0 instead. 2 modes, versus what is regular. Spherical basal functions, what the fuck? So people go with spherical coordinates. Maybe I'm missing something. Quantum normalization of a wave function in spherical coordinates. Okay, Seems like that might be a candidate. So I have been provided with the following wave function. Okay, cool, I like it. I'm trying to convert it to spherical coordinates and to find the normalization constant n. Great. Applying this to the wave function, fine, we don't care about this. My issue, I'm stuck here to calculate the normalization constant that I did take, so okay, so now I have to do the whole thing. yr squared. Or, you see, there's something here missing. I'm very familiar with integration, however, this integral is causing me lots of issues, so I'm wondering, is there a better method of approaching this, perhaps separating the integral more? Any help is appreciated. The two methods are the same. Why r squared though? Because of the angles being different? Why r squared though? Okay. If you're obliged to do the integral in spherical coordinates, then take your expression 1, remembering to include a factor of sinus theta in the integral as Bill and remarked. Now expand. You will obtain many products of trigonometric functions, but this can all be solved by using the standard tricks. After doing theta and phi integrations, you'll be left with the integral of... If you're doing the integral over all space, as I suspect, then it is standard result at the fourth moment of a Gaussian. Okay, there's some clues in here. So, it's easier than this because we don't have all this crap to translate. We don't really need to translate that. We're talking about spherical, so we're gonna stick with spherical stuff. But there's like these basically still triggers like a big question in me, which is this whole thing of like, are we really in 3 dimensions or in 4? Why not in 4 dimensions, you know? But I think we can get rid of these. So let's stick with spherical. I'm confident that we should stick with spherical. And I'm confident that we should that why do they say, so why is it just r squared? They don't put like, then the r d phi. Z is r times cosine. Applying this to the wave function. I'm stuck here. So number 1, these or what is this? What is this y? The angular part. I'm not so sure I understand that. I'm trying to understand the free particle in both Cartesian and spherical coordinates. So a free particle going in, say, x direction with some energy E. We know the wave function of such particle is like this. Now let's do the same calculation in spherical coordinates and derive the wave function. In spherical spherical equations, take the following form with the angular part. This is something new. There's no angular momentum, but okay. The angular part. This is... I probably shouldn't go there. Wave function. Angular part. Okay, so... What is the angular part? Article dummies.com. I like why am I getting so many suggestions on like dummy stuff? I should probably buy this book. Anyway, okay, that's something else that I've learned that okay, so the angular part of a wave function, when you work on problems that have a central potential, with central potential problems, you're able to separate the wave function into angular part, which is a spherical harmonic, and a radial part, which depends on the form of the potential. So when you have a central potential, what can you say about the angular part? The angular part must be an eigenfunction of L squared, and the eigenfunction squared are spherical harmonics, whatever that means. Oh my god. The angular momentum. What the fuck? That's okay. There's definitely something there with the angular part, so that's not so straightforward. But apparently it should be the same. The Normalization condition becomes psi squared r squared sinus of theta. Whatever that is. And version of integration. How this? Okay, so the method's the same. That is correct way of calculating normalization constant n. Yes. If it cannot be part of R since it is not spherically symmetric, is it still possible to calculate the probabilities of physical measurements of angular momentum operators, or is it characterized by this wave function? Oh god, the angular momentum is bothering me now. So if you're obliged to then take the expression 1, yeah, r squared, okay. Remembering to include a factor of sine theta in the integrand, as Bill N remarked. Bill N. Oh, 6 more comments. Bill N. In your first integral, you're missing sin theta factor in the dv equation. Is r squared and sin theta. Sinus of theta. Sin sinus theta. Okay, so that's correct. Sinus of. I said phi is the theta. The math way, the physics way, I don't know. Let's stick to theta. Let's go to these guys. R squared sinus of theta. Bill, and oops, I did the same thing in my comment. I mastered it in spherical coordinates. I can't figure out the integration despite a number of attempts and substitution methods. This should be trivial, which makes me more frustrating. Makes it more frustrating. Yes, tell me. I've been how many hours already on this problem? What am I there? Now expand psi squared. You will obtain many products of trigonometric functions. It's going to solve using standard tricks. After doing the theta integrations, you will be left with the integral of r. So it's telling me to the first theta and phi. The question is, what are the angles for those? If you're doing the integral over all space, as I suspect, then this is a standard result. So first we're integrating these. Okay, so let's do first the integral on phi, on theta and phi, which would be pi and 2 pi. I think those still, you know, matter. Although for physics people, spherical coordinates conventions, I should probably do that as well, right? Quantified part of spherical coordinates. I should probably actually. Oh fuck no! How do I? How do I open the, like, a previously Control Shift T. There you go. Ooh. Okay, so spherical coordinates in physics. So phi, theta is this one. Okay. So theta is, I don't know if I can do, yeah, I can, because we know, let's try to do just theta being pi and then the other one 2 pi. See what happens first with these. First we do, what did I say? First theta. So first thing is theta, we do 0 to 0, 0 to pi. Then we do phi 0 to 2 pi. And then we do r 0 to infinitus, infinite. And then we'll see what happens. Probably nothing. We're fucking almost there. Almost there. We're almost there. And if I do pi halves, oh god, what happened? Formatted. I didn't want to format anything. Nah, then we get this crap. Okay, it doesn't work. It's all overall space. Ah man. Where the mistake is, who knows? Who knows? Alpha is real. R is real and positive. Theta and phi. How do I? That's the thing, right? So how do I? And Z is not needed. I'm confident this is where we should do, the way we should go. I mean, you know, the thing is like, oh, is it the square root of is it like, is square root of fraction the fraction of square roots? Is it really like this? Is this true? Okay, seems like. Okay, so that seems like it's a okay. Because that would actually bring it close, because that would be the same as saying the square root of a. Okay, so we have, this is the solution, right? Maybe this is a fucking typo, you know? That's the other thing. I missed this fucking 3 here. Oh my god. Why is the baby crying now? I don't know. Nobody knows. Anyway, it's like. Because, you know, essentially, it's like saying. Paint. Can I open Paint? right? So if just you know, just in case you don't know what I'm saying, I'm just saying is that if I have square root of a to the power 3 divided by the square root of pi, so this is the same as the square root of a to the power 3 divided by pi, which is the same as saying the to the power of 1/2. But then there is missing a 3 here, like, so it's not really, man, but like that is just, I think it just might be a fucking typo. I mean, you know, this is like, it just can't get simpler than that. I think I'll just have to leave the honor out of my, you know, maybe I'll ask, you know, maybe I'll ask Twitter. Maybe I can ask Twitter. So maybe I'll ask one on Twitter. So this is basically dv. I can just use that to make it a bit nicer. So dv, okay, just dv, and this is basically the wave. It's like psi squared, right? Would be. Just to make it a bit better, a bit nicer. And so we integrate first theta, then phi, and then r, the radius. Maybe that is the problem somehow. Maybe what I will do is, I think I'll just open up I might open up a physics question, stack exchange. I should use that more. I think using these is definitely less like you're asking questions to the internet. It's almost like I should be, yeah, or maybe in Twitter. Maybe I should use Twitter. These, I don't know. It's almost like, maybe I can ask a question. I can ask. I mean, these questions are serious. Like, yeah. So it's like it can be anyhow else. It can be any. It's just easy, you know. Fairly easy the way it is. It's like positive. So we're integrating the volume. The things that I like to understand a bit better, which is like, why does this work? Sort of the product of these kind of works, you know, of these within a sphere. That's the one thing. The second thing is why is you know, is it 2D? Is it 3D? Like, what is the? That's kind of what I'm missing. It's like I'm not really understanding. Maybe in the next session I'll just try to put that in writing and then ask the question in general. I think I just don't know. I don't know why there's a 3 in here. I really don't know. I get the same solution, but I get like 1 divided by 2. So this I really truly don't know. And I don't get it why the 3D works in here. Because my natural inclination would be to think about it, we need 4 dimensions, because, well, because the wave function, it's but it's not that it's a function, right? I think that's it. It's not that it's a function that has values, like a 4th dimensional value. It's more like that function describes it, so that it is already that 3D. It's the wave function in a way tells you it's relating. This is such a problem, because you always tend to think about, at least from a programming perspective, like inputs and outputs, right? And so I think, what's the output of this function, of the wave function, and that will be my 4th dimension, assuming the input is a 3 coordinate point. But it's not. The wave function is just a relation between the coordinates, and what this relation tells you is this relation is implicitly telling you where can this particle be. Like it's telling you, if you're not in these, like if you're in 3D space and it's just, let's imagine a flat plane, 2D plane, everything that is not in this plane are points in 3D space where the particle can be, because they're not part of the wave function. I think that is the way they interpret that, and and this was one of the biggest headaches in my for these, at least initially. Okay, so that's kind of, put that aside. That's good. It's just you imagine you have that kind of cone, right, and then yeah, exactly. That's the shit. Yeah, basically. If this is your wave function, that's where the particle can be, I guess. Also, it's not true. That is also not true. That is the main, it's like the main issue that I have here is I think I was getting that shape wrong. And maybe this is what you have to do. No. I mean, R obviously can just be 0, but 0 is a non-valid number, maybe, because of what the spherical doesn't work well there. But that wouldn't make a difference. I think it's just 0 and infinite. Maybe it's really that n. No, also no. I mean, it's just, forget about this. Anyway, I'll leave it here. But what I mean is, I think that what I mean is, like, for me, this was I think one of the problems is that when we're writing something like these, like we're not really saying that this is a value. We're saying this is the expression. This is what you want to plot. So really what you're really plotting is these how would it be in 2 dimensions? Let me close with these, at least this session, Desmos. I don't know. I don't know if I'm ready yet to wrap up this problem. I definitely will open a question, because I just feel there's either a typo or is just maybe I'm just, this feels like I can't be missing anything here. Maybe I'm making a mistake somewhere here. I don't know. But so what about the what am I doing? So I wanted to check on the shape of these. Let's say exp of, let's say minus 1, okay, minus 1 times square root of like x squared plus y squared. Can I plot? I want to plot these. Plot exp of minus 1 times square root of, and now we have x squared plus y squared. Okay. I mean, I was not okay. I was not, but that's. So what's the equation of a circle? Right, let's say plot x squared plus y squared equals, let's say, 4. Okay, so that this plotting assumes that's the the plotting assumes this is the way this works. Okay, so it's x, y, and then there's a z function that equals these, right? That's the So in reality, if you wanna say square root of these and kind of like that is then also what am I doing? Oh god, I'm having such a mental problem with these. That is definitely 2D, 3D, 4D. Fuck. So the wave function is, in a way, it's something that when we plot in 2 dimensions, we plot a relationship between x and y. When we plot in 3 dimensions, we plot a relationship between 3 different functions, right? 3 different variables. I don't know. I have to think. I don't know. Next time. But I'm like, I don't know. I really can't do anything better than this. This feels the standard way, and the path to get here has been just too much like that, focusing on stuff that doesn't really matter, I think. But I mean, at least I've learned a couple of things. Let's see. I'll try to wrap up in the next video. Okay, promise.